Okay, so today's subject on this topic of finite element accuracy and discretization error will continue from where we left off last time when we were discussing particular solutions to two-dimensional elasticity problems. And I pointed to this specific example, kind of an interesting one of a plate with a hole. And the most interesting thing about this problem is that at least in this particular setup, we can emulate the behavior of this plate having finite dimensions with a hole in it, to which we prescribe this external traction load, a tensile traction to this, circular hole embedded in this plate. We can visualize what's the resulting distribution of internal stresses that arise within this plate under this external tensile loading. And we noticed some interesting behaviors. We noticed that there's this maximum stress that occurs right at the edge of the hole, maximum tensile stress at the top edge of the hole, maximum compressive stress at that bottom edge of the hole. And the whole behavior of this plate deforms in such a way that the hole itself deforms in this ellipsoidal fashion. It contracts in the y direction and it expands in the x direction. And some of the reasons for why it does this, have to do with the way that stresses distribute through bodies, now considering this general theory of elasticity and solving it approximately using finite element methods. However, the one thing that I want to point out, even though we can set up this problem, define all the boundary conditions, run our finite element analysis, and kind of interpret the results, we can do all that. But we didn't have to in the end for these types of problems. And in fact, for this specific problem, or a slight variation on it, it turns out that there is an exact analytical solution that we could obtain just using the classical theory of elasticity. It's a bit limited to the particular case of a large plate or a practically infinite plate in size with a small circular hole embedded in the middle of it. And we could prescribe external tensile tractions to the edges of this plate, at the far, far away boundaries of this plate, having infinite dimensions. And it turns out under those special circumstances, assuming plate and stress conditions and other things like that, we can derive an exact solution. And the details of that are not something that we're going to go into in this course. I'll just present you with the fact that it's possible to derive such a solution that exactly satisfies equilibrium in this pointwise sense. And the main thing that I want to point out is that this exact solution satisfies the original strong formulation of this elasticity boundary value problem. So rather than solving, the weak formulation, going through all those machinations that we tried to do to manipulate things into the format of, a weak formulation that we could approximate using a Galerkin scheme, these solutions actually satisfy the original strong formulation. Very difficult to come up with these solutions, but if you have them, they're extraordinarily powerful. And in particular, they're really useful if we want to come back and evaluate how good is our finite element solution in comparison to what we know the exact solution to be. And that's precisely the subject that we'll dive into in today's lecture. We're going to compare these results, what we expect the exact solution should be for the stress distribution in this plate, and compare it against our finite element solution. So let's actually kind of see what exactly does the exact solution look like. And the important thing to note here, and you can kind of take a look at the exact solution for this, infinite plate with a circular hole by considering this simple MATLAB script that I've actually uploaded to Canvas. So if you go to the Canvas page, there's some MATLAB examples that I've uploaded, including this one that plots the visualized result of what these different stress components should be and how they vary throughout this plate. And you'll notice some interesting features of the solution. It emulates a lot of the things that we already saw in our finite element analysis, right? We noticed some interesting things like the stress near this edge of the hole achieves a maximum value. There's some other things like the compressive stress at this kind of outer edge of the hole also achieves some maximum value, indicating that indeed the plate is contracting in the way that we saw in our plotted results for our finite element analysis. And there's some variation in the shear stress that's kind of interesting as well. But the main feature that I want to draw your attention to is precisely what this value of stress, the maximum tensile stress in the plate is relative to that distributed traction load that we might apply to the far field boundaries of the plate. So if we applied some uniform tensile traction far away from the hole to this plate that has a magnitude of what I'll call sigma naught. So kind of, you could think of it as the nominal stress is sometimes what it's called. This nominal stress value, I've normalized it such that it has just a value of 1 Pascal in this particular example. And what we notice from this reference solution, the exact solution, is that the magnitude of the maximum stress in the vicinity of the hole is roughly 3 times the nominal stress. That's what we expect to see. And you can actually characterize this in a non-dimensional way by defining something called a stress concentration factor. This is useful not just in the case of this example of a plate with a hole, but in general, if you have, let's say, some kind of structure or some kind of member that's subjected to tensile loading or some other type of loading, you can define a stress concentration factor that defines what's this maximum stress that might occur in some part or structural member relative to the average or nominal stress that we're applying to this member, maybe at its ends or something like that. And it's useful for design purposes because it gives you a sense of, what's the maximum stress that would occur at any interior point within this, plate with a hole or some other structural member that has some kind of chamfered edge or some other feature that you want to try to limit what's the maximum stress that would occur within this member. So clearly for design purposes, you want to limit what that maximum stress is going to be such that you prevent the material from yielding or fracturing or doing something else that you don't want. All right, so you can define the stress concentration factor. It's just the ratio of the maximum stress to this nominal stress value. In this case, that stress concentration factor is just 3 times the nominal stress. Okay, well, if we can define that's what we expect this stress concentration factor should be for this exact solution of this infinite plate with a circular hole, what exactly does our finite element solution tell us? How does it compare to what this predicted maximum stress value should be? Well, let's take a look. So comparing side by side these different solution fields for the axial tensile stress in the plate, the YY vertical component of stress and the shear stress, we can see here is basically just at a high level the plotted solutions, normalizing the stress ranges for these color plots such that they're the same in each one of these different comparisons. We see that by and large they look pretty similar, at least. So that's good. At least we see the same patterns emerging, that there's this concentrated stress happening at the interior of this hole, and both in tensile loading and in compressive loading at different edges of the hole. We see more or less the same variation in shear stress throughout the plate. So a lot of those kind of high-level details seem to be similar. So that's good. At least we're getting qualitatively similar answers between the exact solution and our finite element solution. That's good. We want to make sure that whatever solution we get from our finite element analysis, at least it seems to be in agreement with the exact solution. But let's actually look at what's this maximum stress right in the hole according to our finite element analysis. And what we find is we could compute the stress concentration factor in the exact case, compare it to what's the approximate stress concentration factor determined by our finite element analysis. And what we find is that this maximum stress relative to the nominal stress is, basically given by the stress concentration factor, roughly 2.67, not quite 3. Now, that might be a little bit of a cause for concern, because clearly, if we're trying to use finite element analysis in lieu of our actual exact analysis, in order to design some mechanical part or design some structural member such that it never exceeds some maximum stress limit, then clearly our finite element analysis would seem to be saying that, well, this maximum stress is only 2.67 times the nominal stress, lower than what the exact answer should be. It should be 3, which means that if I had a factor of safety on this thing that kind of said, well, this looks good. Maybe, my maximum stress intensity factor for design purposes, what if I said it was 2.8? I didn't want the stress to exceed, a factor of 2.8 beyond the nominal stress. According to my finite element analysis, I'm good. But in reality, the true maximum stress is a factor of 3 beyond the nominal stress. So that's a problem. Obviously, for design purposes, this isn't giving us a conservative result. So what gives? You know what? The finite element solution, it's kind of like underestimating that maximum stress. So obviously that's a concern. But we want to know, is there a way that we can at least say, reduce this error, this apparent error between the exact solution and our finite element solution? Is there some kind of rationalization for, either why that's happening, or can we at least figure out, is there a way to get around this problem? So that's the question. How do we quantify the error, in other words, between these two different solutions, and then figure out how do we minimize that error? Or are there any guarantees that tell us, what's a reasonable way to approximate this solution? And when is it appropriate to use finite element analysis, and when can we trust the results? Okay, so that's really our goal here. But before we get into some of those details of how do we quantify error, we really have to account for what are the possible sources of error in running a finite element analysis. And there are quite a number of them. So I've provided a pretty comprehensive list here that points at all the different possible places where maybe some error could have creeped in to explain why this value for the stress concentration factor is lower than this value. And it spans a bunch of different things. We've already talked a little bit about one of them. We talked about finite precision arithmetic and numerical round-off errors, things due to basically truncating numbers and carrying out computations on a computer that can result in these kind of precision errors when we're actually multiplying and adding and subtracting numbers from one another. And that can accumulate to the point where we actually end up with some error. Now, in general, I want to point out that even though I highlighted the finite precision arithmetic accounted for why that simple patch test solution that I presented in the previous lecture, it accounted for why the stresses weren't exactly 0 when they should have been 0 in that simple patch test problem. That said, they were still really, really small. I mean, almost like 10 to the minus 16 smaller than the nominal kind of applied tensile stress in the problem. So in general, I want to point out that even though finite precision arithmetic does show up, oftentimes it's not a significant source of error in a lot of cases. Sometimes it can become a problem, but for most day-to-day analyses, it's not something that you worry about. It's not the biggest source of error that we care about. So we can kind of cross this one off the list. It's probably not the reason why we're getting such differences between these two solutions. But there are other possible ways that we could be introducing errors. There's discretization error. That's basically a consequence of us choosing to represent our solution in our finite element context as this kind of approximate representation of a discrete solution field consisting of a finite number of basis functions, our finite element basis functions. And choosing to represent this solution using a Galerkin approximation method limits the ability of our solution to be able to represent more complicated, functional representations of what we think the solution should look like. So that characterizes a pretty significant source of error. There's also just error in representing the geometry itself. You can kind of imagine in this plate with a hole example, we're sort of approximating the curvature of this hole. It should be a perfect circle on the interior. But if we used a coarser mesh, if we used fewer elements to discretize this plate, you can kind of imagine the segmented representation of that interior curve is going to look not such, like a smooth curve. It's going to look like a piecewise linear segmented, approximation to what this actual geometry should look like. And that can happen if you're trying to represent these kind of nice smooth curves with these piecewise linear edges of the finite elements that you use to discretize a problem. It can also show up if you're trying to reduce the level of detail in representing some kind of part that you're modeling. So if, let's say, there was some very fine scale detail, maybe like an even smaller hole embedded in the mesh, but I don't have the level of refinement in my mesh to be able to capture some of those details, I may have to de-feature those things and just eliminate them and not even try to represent them with respect to the finite element geometry and the resulting discretization. So you have to make approximations in representing the geometry. And that can also introduce errors, potentially, which account for some of those things that we see here. There's also numerical integration. All the computations that we've laid out to compute element stiffness matrices, to compute external forces and their contributions to the global system of equations, we're using numerical integration to approximate these integrals using, Gaussian integration or whatever. And depending on the number of integration points we use to approximate those integrals, we could potentially be introducing some error in approximating what's the stiffness of individual elements and things like that. So that's a possible source of error. Another one I'll point to is when we actually go to solve the resulting system of equations, that Ku equals F, that matrix inversion procedure can be done actually in a number of different ways. We can just tell MATLAB, invert this matrix. And, at the end of the day, it's up to MATLAB to decide how exactly it does that. But it's worth noting that there are actually multiple ways that you can solve systems of equations in this numerical context. If you're familiar with inverting a matrix by hand, there are ways that you do that that involve methods such as Gaussian elimination, which is a procedural way of trying to do these computations by hand to analytically invert a matrix. However, there are ways that you can solve a similar system of equations not by doing those kinds of direct solution procedures like Gaussian elimination, but instead using approximate or iterative techniques to try to invert matrices. And that becomes really important, especially if you're trying to solve really, really big systems of equations, in which case those classical direct solution methods like Gaussian elimination and its similar derivatives, actually it becomes really difficult to solve those problems in a tractable amount of time. So people have invented these iterative solution techniques like a conjugate gradient method, Jacobi iteration methods, Gauss-Seidel methods. Under the hood, that's possibly what some of these finite element solution procedures are actually using behind the scenes. And it may not be evident that, that's what those programs are actually doing. It is important to note, however, that that can also introduce a source of error. If we're approximating the solution of these linear systems of equations through some iterative procedure, we're not exactly actually solving the original linear system of equations, the finite element system of equations that we've assembled. We satisfy it within some residual tolerance that might be specified by these kind of linear solution procedures, but we don't exactly satisfy the original Ku equals F. There's going to be some residual error that manifests when we apply these different methods. So a bunch of different places where error can creep in. Partly it's due to the numerics, partly it's due to the algorithms that we use to solve different aspects of these problems. And it gets even more complicated if we introduce other complexities into the analysis. If we're solving, let's say, a time-dependent problem or a dynamic problem that involves not just discretization in space, but potentially discretization in time, in which case you may have to introduce some kind of discrete snapshots to represent the solution at discrete points in time, sometimes called time steps. And there are methods specialized to the solution of these time-dependent problems that involve figuring out how do you translate the solution at one time state to the corresponding solution at the next time state, sometimes called time-stepping algorithms. And there are a bunch of different ways that you can solve those types of problems, but they all incur at least some error as you try to advance the solution from one time to the next. Other interesting things arise when you introduce nonlinearities into the problem. Here too, not just in the solution of these iterative linear systems of equations, if you're trying to solve a nonlinear system of equations now, there's even more iteration to try to approximate the satisfaction of these Ku equals F systems of equations, because no longer are they representable truly as Ku equals F. They're represented as a nonlinear relationship between force and displacement. And that introduces a whole lot of complexity. Typically, people use things like Newton-Raphson iteration methods and other types of methods like that that, further blur the line between what exactly is a good enough solution and one that exactly satisfies my original set of equilibrium equations. So all these different things can introduce significant error. However, at least in these simple problems like the one that we're considering in today's lecture, we can kind of cross off the list most of these different sources of error and say, well, we're doing the best we can in representing the geometry. We're not defeaturing it too much. We're doing a reasonable job in capturing that curvature. We're using a sufficient number of integration points. It turns out numerical integration, even though we're approximating these integrals, it does actually a surprisingly good job in making sure that we're not introducing too significant errors here. If we're using a MATLAB or some other kind of numerical tool like that, we can be specific in choosing methods that give us ways of solving these systems of equations that don't introduce error by trying to solve things in an approximate sense. We can instead insist that we're going to use a direct solver that uses these classical Gaussian elimination techniques. So we get rid of that. Finite precision arithmetic, it's always going to be there, but it's going to be small most of the time. And as long as we're not solving anything too complicated or nonlinear or time dependent, then certainly that's not an issue. So really the main thing that we're left with as the primary source of error for at least a lot of these simple linear analyses is the first one, discretization error. The error that we just can't get around because it's inherent to the way that we've chosen to represent our solution as this kind of finite element representation of the solution field, as this interpolated field that's connected to our discretization at the end of the day. And we can't do any better than that. So really, this is the one that we're going to focus on, and it tends to be the one that dominates the solution error. So really what we want to know is, how bad is the error depending on how we've chosen to discretize the problem? Can we make some kind of assertions about the level of accuracy that we should expect out of our finite element analysis dependent on how fine or how many elements we're using? That's the relationship we want to establish. Is there a way of connecting accuracy or error in our solution to the number of elements that we use? So in order to pursue that, we have to define some metrics on what we mean by the level of refinement in our mesh. And typically the way that we do this is by defining some parameter, which I'll call h, which establishes a characteristic size of the elements in our mesh. And typically h measures something like the diameter of the largest element in our mesh. In this case, I'm not really picking off the largest element. I think this is probably one of the smaller elements in the end. One of the larger elements would probably be out here. But it's just to give you an idea that really h characterizes something about the maximum size or the average size of the elements that I'm using to discretize this problem. And you can certainly imagine that that element size, h, can be connected in some fashion to the number of elements that I'm using to discretize this geometry. So I could define it in terms of the number of elements that I'm using to discretize this thing, or I can define it in terms of this element size parameter, h. And you'll notice throughout the rest of the lecture, I'll use this h parameter to denote that, if I'm solving a problem using finite elements, then I can find the solution, a finite element solution, which I'll denote with this u with a superscript h, which basically means my finite element solution given a mesh consisting of elements with characteristic size h. And that h value could be, a larger value, it could be a smaller value. So typically, you can think of these finite element solutions as being dependent on the choice of element size h in almost a continuous way. If you think of, refining this mesh with more and more elements, you're changing that characteristic element size. And in a way, you could almost think of it as this extra dimensionality parameter that characterizes finite element solution as a function of element size h. That's kind of one way to interpret this. All right, so what we seek is a finite element solution representable in terms of some finite number of these nodal basis functions, the phi sub a's. And we also notice that our finite element solution, as we've talked about in previous lectures, is really just an approximate representation of what we think the true solution should be. But in general, the exact solution to this problem may exist in some larger space of functions. Really, if we're prescribing the original strong formulation, or in this case, the weak formulation of the boundary value problem that we sought to solve in the beginning, we note that really, the solution that we seek lies in this very general space. It might lie in H1, the space of all possible H1 functions that have, basically they're L2 integrable, and their first derivatives are also L2 integrable. So it's a very general space of functions, and it basically encompasses an infinite number of possible functions that satisfy those requirements. So really, the exact solution may live in this very, very large dimensional function space, whereas our finite element solution is constrained to lie in this finite dimensional function space that's parameterizable in terms of that element size, h. So typically, we can write exactly what we mean by that previous assertion by saying that our true solution will lie in this much larger infinite dimensional function space, which I'll just denote with this calligraphic U symbol. But in general, the space of functions that we're using to try to represent our finite element solution, this calligraphic U with a superscript H, that subspace is a finite dimensional, function space that is, it still belongs to this same set of H1 functions, but in general, it's a smaller subset of that infinite dimensional space that the true solution might live in. So really, what I'm saying here is that, the true solution, it could be any possible function. Ahead of time, we don't really know where it's going to live. And our finite element space of functions is this kind of smaller dimensional, finite dimensional function space that is nonetheless a subset of this broader class of functions that the true solution belongs to. Now, we provided some definitions of, what exactly can we provide as a guarantee that our finite element solution is nonetheless going to be at least a reasonable approximation of the true solution. And we defined this best approximation property that said, even though I'm constraining my finite element solution to belong to this smaller subspace of functions used to represent this approximate solution, it nonetheless gives me the best approximation amongst all possible functions that lie in this constrained subspace of functions. So it's the best that we can do with our finite element discretization that tries to approximate the true solution. But sometimes the best that our finite element solution could do is still not quite good enough. Nonetheless, we can say that our finite element solution belongs to this finite dimensional subspace, U superscript H, that is still a subset of this larger space of functions. All right. Now, the thing that I want to define at this point is, how do we actually measure solution error? We introduced some of these definitions actually in a preceding lecture, the same lecture where we discussed this Galerkin best approximation property, and it involved defining some kind of measure of the difference between two different functions, in the same way that we might define some distance between two vectors that lie in a vector space. We can define these function norms or measures of the size of some function to establish what's the magnitude or what's the size of a given function. And we could define actually a few alternative descriptions of this so-called function norm that might satisfy the following different identities. So the two ones that are most commonly employed are this so-called L2 norm on a given function, which is sort of something that looks a bit like this. In a discrete sense, you can kind of intuitively think of this L2 norm as being something like the sum of the squares square rooted. Very similar in some respects to taking the magnitude of a vector, right? You take the sum of the squares of the individual components of that vector, and then you take the square root of that thing, and that gives you sort of the length of that vector. In the same fashion, we can define a function norm in this way by supposing that we define a similar operation, but just recognizing that no longer do we have discrete components of a vector that we have to square and then sum together. We have a continuous function. And in order to do sort of a similar operation, we actually have to integrate this function, multiply it against itself over the entire domain where that function is defined, and then take the square root of that thing. And that gives us this definition of the L2 or displacement norm. It gives us a measure of exactly how far away is this function on average away from a state of just pure zero displacement everywhere. So the L2 displacement norm gives you a measure of what's kind of like the average displacement throughout the entire mesh, if you like. And the other one that we might define is this so-called H1 energy semi-norm. So-called because it turns out you can define this measure of a given function sort of similar to the way that we define energy in the context of mechanics. So if we have, let's say, some definition for displacement field U, we plug it into this definition that involves a similar integration over the domain, but instead of U dotted with itself, it's now the gradient of U multiplied by the material stiffness, and then again, inner product with the gradient of U, which it turns out to be equivalent to just taking a measure of the stress multiplied by the strain, all their individual components individually multiplied by each other and summed together, and then take the square root of that whole resulting expression after you integrate that over the entire mesh. And it turns out that the interior term, that integral term, provides a measure of the total internal elastic strain energy in the mesh. So in a way, this H1 energy norm is a measure of the elastic strain energy, the total strain energy in the problem. Okay, now given these different alternative definitions for function norms, the L2 norm and the H1 semi-norm, we can use these definitions to also measure not just what's the magnitude of a given function, but also what's the difference, what's the magnitude of the difference between two different functions. And we can apply this in particular to measure what's the error between our, let's say, our exact solution, which I'll just denote with U, and maybe an approximate solution, UH, corresponding to our finite element solution. So we can measure what's this solution error, U minus UH, in either of these two norms, either in the L2 displacement norm or in this H1 energy semi-norm. Now, they're both perfectly valid ways of measuring error, but what does this kind of tell us? And how do we actually measure, let's say, some of these norms and apply them to that problem that we were considering, the plate with a hole problem? Well, suppose that we did this. Suppose we had some sequence of meshes that we could use to solve that same problem, and we can choose in each one of these different meshes to measure what's the corresponding element size in this sequence of meshes where I'm reducing the size of the elements on average. So the first mesh, I might have relatively large elements. And the second sequence of meshes, maybe I took the original element here and subdivided it into 4 smaller elements. So H2 is nominally half of H1. I could do that again. So H3 is nominally half of H2 and so forth. H4 is half of H3. And I can do this continuous sort of refinement procedure, choosing to discretize my mesh into a smaller, and smaller elements, using more and more elements to represent this structure as a whole. And what I find upon doing this procedure, as I shrink the size of my elements to be, smaller and smaller, almost approaching an element size that tends towards 0 in the end, what I find is I can measure things like, what's that stress concentration factor that I was looking at previously, the ratio of the maximum stress, let's say, in this element relative to the applied external stress. And what I find is, the original value that I got here for this coarse mesh is pretty bad. It's like 2.37. It should be 3. But if I use, let's say, an element size that's half of H1, I get a little bit better. It's 2.67. And if I keep going, now it's 2.84. And then now it's 2.924. So clearly, if I'm using more elements, I'm getting closer and closer to what I expect that kind of value should be for that stress concentration factor. It seems like it's moving towards the right value, the expected value of 3. And I could measure the error relative to this kind of maximum value of stress in the mesh. But it turns out that that's not usually a good way to measure error. Trying to measure what's the error in measuring the displacement at a single point, or measuring the error in the stress at a single point. You can't actually guarantee that that measure of error localized to a single point within this domain will actually converge to any given value. The only way that you can provide and guarantee that you're going to converge in any given error measure is by using one of these standard error measures, either the L2 error norm or the H1 energy semi-norm. And we could choose instead to look at what those measures of error are as a function of this element size H. So the plot on the right actually shows what would you expect to see if you were to compute those different error measures between the finite element solution, where H is a variable parameter that we might choose to continuously refine. And we can see that, on the x-axis, I'm plotting not only the element size, H, and on the vertical axis, I'm plotting this error measure. Instead of actually plotting it on a linear scale, however, I'm going to do something funny. These typical error plots are usually plotted on a log-log scale. So rather than H on the x-axis, it's more like log H. And instead of the error on the y-axis, it's more like the log of these different error measures. And what we find is that as we increase the number of elements, as we decrease H, in other words, as we kind of decrease H along this dimension towards H equals 0, basically right at this point almost, what we expect to see is that, the error should also be decreasing, almost down to this kind of origin point. And we see that that is true in both of these different alternative error measures, the L2 error and the H1 error. We could evaluate for each one of these different meshes and these sequences that the L2 error diminishes as I continuously decrease the element size, and so too does this H1 error measure, but they do so at slightly different rates. Now, what's interesting about these plots, if you were to do this exercise, is that you would notice, at least in this log-log plot of the error versus element size, that it seems like you could almost draw a straight line between these different points, measuring, element size versus error. And that's generally true. Typically, this is a good way that you can verify, am I actually converging to the right answer? What you should expect to see is that in this log-log plot, you should see a roughly linear relationship, but the slope of that line will have maybe different magnitudes depending on which particular error measure you're looking at. In this case, if you were to do this problem, you notice that the L2 error actually converges at a rate that it has a proportionality of roughly 2 to 1. So the error will decrease by a factor of 2 for every kind of factor that you've reduced the element size. By comparison, the H1 error will diminish at a roughly rate of 1 to 1 with respect to decreases in the element size. So what gives? What's the deal here? I mean, we'll have to actually demonstrate this a little bit later, but the main consequence that we see, if we intend to make this observation, and we say that, or at least we're diminishing, it seems like we're diminishing at a constant rate in both of these different error norms. What we can take away from this is that if we assume that those trends continue, what we conclude is that in the limit, as H becomes smaller and smaller, as we continuously refine this mesh, we do anticipate that the error will tend towards a 0 value, which is equivalent to saying that in the limit, as H goes to 0, we expect that the errors should also go to 0. And that's an important consequence. And it's important also to observe that, we can certainly do this experiment. We can observe how the error changes with respect to mesh size. But even more important than that, it's actually possible to show mathematically that these statements are true. At least if I'm using a finite element approximation, there is a way to actually relate what's the estimated error in these different norms and express it as a function of this element size. And then based on those estimates, we can actually show that as H goes to 0, it's possible to prove that this is true. And that's a hugely important consequence for finite elements. It's essentially a guarantee that as long as you use enough elements, you will converge not just to some solution, but to the exact true solution that you would expect from solving the original elasticity problem. Not all methods guarantee that. Not all kind of numerical approaches will give you this kind of strong guarantee that you will get not just a solution, but the right solution. So that's kind of part of the reason why finite elements have been really important in solving engineering problems. They provide these definite guarantees on solution accuracy, in other words. Now, I want to point out why exactly do we get such good approximations in the limit as we continuously refine the mesh. And to really explain that, we have to dive into a little bit of the details of what exactly are finite element basis functions doing, and how well do they approximate other types of functions that we might want to represent. And the best way to define exactly what we mean by the ability of the finite element shape functions to reproduce some other function of interest, to define that, we have to define this new term, which I'll call polynomial reproducibility. It's effectively a statement that says, if I have some set of finite element basis functions, these phi sub a's, then given some other function, which I'll call f, which maybe it's some polynomial, then if my finite element basis functions are capable of reproducing that particular polynomial function, it's equivalent to effectively this statement here, which says that I can take that polynomial function, I can evaluate that function, the corresponding nodes of my finite element mesh, and then I can interpolate those evaluations of that function at the nodes, and what I get back should be the original polynomial function that I kind of put into this expression. And if I have, let's say, polynomials up to some particular degree p, my finite element basis functions, if they satisfy this condition up to degree p, then it should be possible to plug in any possible polynomial of maximal degree, let's say 2 in this example, where p equals 2. And I should guarantee that not just will I, get a reasonable approximation to that polynomial, but my finite element basis functions will be able to exactly reproduce that same original polynomial. Now, that's a lot of math expressions. I want to, heuristically demonstrate what does this look like in the context of some of the shape functions we've looked at previously. So, for example, linear finite element shape functions, basically these kind of simple piecewise, functions that allow me to interpolate discrete values using just simple linear, interpolation between discrete nodal points. I can use these nodal shape functions, these linear shape functions, to try to do exactly that procedure that I described. So given some function f, I could suppose, I could take discrete evaluations of this function at the corresponding nodes of a given element. And given these different discrete values, I can then attempt to use my finite element shape functions to represent the interpolated function f, which I'll call f superscript h. It's my finite element approximation or attempt to interpolate this original function just by taking these discrete evaluations of f at the nodes. In this case, you can see that because my linear finite element shape functions aren't capable of representing this nice curved function, my interpolated representation f superscript h doesn't reproduce the original function. So it fails to satisfy that kind of reproducibility condition. However, if I look at some other functions, let's say a constant function or a linear function, as shown in these first two figures on the right, you'll notice at least my finite element shape functions do correctly reproduce each of those different types of functions. If I go one order of polynomial higher to try to represent a quadratic function, now, it's game over. I can't reproduce quadratic functions, but I do guarantee that at least if I'm trying to represent any kind of maximal polynomial of degree 1, any linear polynomial, in other words, my finite element shape functions, in particular my linear finite element shape functions, will correctly reproduce either constant functions or linear functions. All right. Now, consider the quadratic shape functions that you looked at in a previous assignment. Effectively consists of an element with 3 nodes, and you've defined the shape functions, which hopefully you maybe even remember from that assignment. We could do this same procedure and look at what's the reproducibility of these quadratic shape functions. So look at the same function, evaluate that function at these now 3 nodal locations, and attempt to interpolate it using effectively a parabolic curve. Now, we still don't do a good job with this function, but we do notice that at least if we're trying to represent quadratic functions now, we have this extra node to play around with. So we can correctly represent polynomials up to degree 2 in this case, quadratic functions. And any quadratic function is therefore representable using some linear combination of our finite element shape functions. You can extend this same concept to look at what's the reproducibility of, 2-dimensional finite element shape functions in trying to represent constant functions that vary as a function of both x and y, and also linear functions that might vary either with respect to X, let's say, to represent some inclined plane, or, with respect to Y. And it turns out that for, let's say, a 4-node quadrilateral element, such an element is actually possible to represent any possible linear polynomial function with respect to either X or Y. And that's a pretty important consequence. In the case of two-dimensional polynomials, it turns out that the space of polynomials actually grows almost exponentially. In the case of, let's say, a two-dimensional polynomial that could be represented as a function of both X and Y, when we speak of polynomial completeness, when we speak of representing some generic polynomial function of maximal order P, we have to include all of the different polynomial terms, not just that include things like X squared and Y squared, but potentially any mixed polynomial terms that include mixed powers of both X and Y raised to different orders. And as long as the sum of the exponents equal this particular order of interest, in this case 2 or 3 or 4, then we basically have to say, if I'm going to try to reproduce polynomials up to some particular degree, then I can't just satisfy only X squared and only Y squared. I actually have to satisfy all of these in order for my polynomial reproducibility conditions to be satisfied. And it turns out that, at least in the case of quadrilateral elements, they at least satisfy this condition of being able to reproduce a linear polynomial. I can reproduce X and Y. I can even include XY, this extra term, but I don't have the ability to reproduce X squared functions or Y squared functions. You could take that to, further extremes and note that actually, if I were to construct some quadratic or biquadratic quadrilateral element, it would be able to reproduce any of these functions in this square. But it only is able to reconstruct the complete set of all the quadratic polynomials, even though it can still construct some of these kind of third order terms and this 1/4 order term. It's not complete in the sense that it doesn't actually have the complete set of, these X and Y cubed terms or some of these other kind of fourth order terms. You can kind of extrapolate what's going to happen if you increase the order of interpolation of these two-dimensional elements, almost to the point where you notice that, interestingly, the order of polynomial reproducibility of these different elements will actually, lead to some interesting consequences when it comes to trying to characterize what's the solution error in these different measures of error as we've previously defined, either the L2 error or the H1 error. And the main consequence that I'll kind of briefly state before I let you go today is that it turns out that the order of polynomial reproducibility of a given element's shape functions actually dictates what's the corresponding rate at which the error will diminish as I decrease the size of the elements in the mesh. So if I use simple first order or bilinear shape functions, I'll converge to 0 error as I continuously decrease the element size, but it'll only kind of decrease at this rate of roughly 1-to-1. If, however, I use biquadratic elements, who are polynomially complete up to a degree 2, then I actually increase the rate at which I would diminish the error up to now a ratio of 2-to-1. And the trend continues. These bicubic elements converge at a rate of 3-to-1. So clearly, what we conclude is that not only do we diminish the error, clearly as h goes to 0, for any of these elements, we guarantee that we're going to converge to the right answer. But also, we notice that the rate at which they converge depends on this kind of polynomial reproducibility, or the degree to which each of these different elements are able to approximate polynomials up to some particular order. So that's where we'll leave it today. If you have questions, feel free to follow me to office hours. But otherwise, I'll see you all on Friday. All right.